Hello, welcome to my presentation video on general information on sizing and protection of conductors. My name is Martin Hlavačka, and in this video I'm going to talk about methodology and definition, overcurrent protection principles, particle values for a protective scheme, location of protective devices, and conductors in parallel. Methodology and definition. Following a preliminary analysis of the power requirements of the installation, the study of cabling and its electrical protection is undertaken, starting at the origin of the installation through the intermediate stages to the final circuits. The cabling and its protection at each level must satisfy several conditions at the same time to ensure a safe and reliable installation. For example, it must carry the permanent full load current, normal short-term overcurrents, and not to cause voltage drop that likely result in an inferior performance of certain loads. Moreover, the protection devices must protect the cabling and bus bars for all levels of overcurrent up to and including short circuit currents, and ensure protection of persons against indirect contact hazards, particularly in T-end and IT earth systems, where the length of circuits may limit the magnitude of short circuit currents, thereby delaying automatic disconnection. The cross-sectional areas of conductors are determined by the general method. Apart from this method, some national standards may prescribe a minimum cross-sectional area to be observed for reasons of mechanical endurance. Particular loads require that the cable supplying them be oversized and that the protection of the circuit be likewise modified. On this slide, you can see a flow chart for the selection of cable size and protective device rating for a given circuit. Maximum load current. At the final circuit level, this design current corresponds to the rated kVA of the load. In the case of motor starting or other loads that take a high inrush current, particularly where frequent starting is concerned, the cumulative thermal effects of the overcurrents must be taken into account. Both cables and thermal type relays are affected. At all upstream circuit levels, this current corresponds to the kVA to be supplied, which takes into account the diversity and utilization factors Ks and Ku respectively as shown in figure G2. Maximum permissible current is the current that the cabling for the circuit can carry indefinitely without reducing its normal life expectancy. The current depends, for a given cross-sectional area of conductors, on several parameters: constitution of the cable and cableway, ambient temperature, method of installation, and influence of neighboring circuits. An overcurrent occurs each time the value of the current exceeds the maximum load current for the load concerned. This current must be cut off with a rapidity that depends upon its magnitude if permanent damage to the cabling is to be avoided. Overcurrents of relatively short duration can, however, occur in normal operation. Two types of overcurrent are distinguished. The first is overloads. These overcurrents can occur in healthy electric circuits, for example, due to many small short duration loads that occasionally occur coincidentally, like motor starting loads and so on. If either of these conditions persist, however, beyond a given period, the circuit will be automatically cut off. The second is short circuit currents. These currents result from the failure of insulation between live conductors and between live conductors and the earth in any combination. Overcurrent protection principles. A protective device is provided at the origin of the circuit concerned, acting to cut off the current in a time shorter than the given by the characteristics of the circuit cabling, but allowing the maximum load current IB to flow indefinitely. The characteristics of insulated conductors when carrying short circuit current can, for periods up to 5 seconds following short circuit initiation, be determined approximately by the formula described below. Practical values for a protective scheme. The following methods are based on rules laid down in the IEC standards and are representative of the practices in many countries. A protective device functions correctly if its nominal current or its settings current IN is greater than the maximum load current IB but less than the maximum permissible current IZ for the circuit. This corresponds to the zone A in the figure. Its tripping current I2 setting is less than 1.45 IZ, which corresponds to the zone B. The conventional setting tripping time may be 1 hour or 2 hours according to local standards and the actual value selected for I2. For fuses, I2 is the current that will operate the fuse in the conventional time. Its three-phase short-circuit fault current breaking rating is greater than the three-phase short-circuit current existing at its point of installation. This corresponds to the zone C. Protection by a circuit breaker. By its high level of precision, the current I2 is always less than 1.45 of nominal current, so that the condition I2 less than or equal to 1.45 IZ will always be respected. If the circuit breaker itself does not protect against overloads, it is necessary to ensure that at the time of the lowest value of short circuit current, the overcurrent device protecting the circuit will operate correctly. Association of different protective devices. The use of protected devices which have fault current ratings lower than the fault level existing at their point of installation is permitted by IEC and many national standards if there exists upstream another protective device that has the necessary short circuit rating and The amount of energy allowed to pass through the upstream device is less than that which can be withstood without damage by the downstream device and all associated cabling and appliances. In practice, this arrangement is generally exploited in the association of circuit breakers or fuses, the technique known as cascading or series rating, in which the strong current limiting performance of certain circuit breakers effectively reduces the severity of downstream short circuits. Location of protective devices. The general rule is that a protective device is necessary at the origin of each circuit where a reduction of permissible maximum current level occurs. Possible alternative location in certain circumstances. The protective device may be placed partway along the circuit. If AB is not in proximity to combustible material and if no socket outlets or branch connections are taken from AB. Three cases may be useful in practice. In case 1 in the diagram, AB is less than or equal to 3 meters and AB has been installed to reduce the practical minimum the risk of a short circuit. In case 2, the upstream device P1 protects the length AB against short circuits. And in case 3, the overload device is located adjacent to the load. This arrangement is convenient for motor circuits. The device constitutes the control and overload protection of the motor, while the short circuit protection is either a circuit breaker or fuses type AM. In circuits with no protection, either the protective device P1 is calibrated to protect the cable S2 against overloads and short circuits, or where the breaking of a circuit constitutes a risk, for example, excitation circuits of rotating machines, circuits of large lifting electromagnets, or the secondary circuits of current transformers. No circuit interruption can be tolerated, and the protection of the cabling is of a secondary importance. Conductors in parallel. Conductors of the same cross-sectional area, the same length, and of the same material can be connected in parallel. The maximum permissible current is the sum of the individual core maximum currents, taking into account the mutual heating effects, method of installation, etc. Protection against overload and short circuits is identical to that for a single cable circuit. The precautions should be taken to avoid the risk of short circuits on the parallel cable line. Additional protection against mechanical damage and humidity by the introduction of supplementary protection, and the cable route should be chosen to avoid proximity to combustible materials. This is the end of this presentation. Thanks for watching.